In today's lesson, we are going to be discussing nomenclature and properties of the following organic functional groups: carboxylic acids, alcohols, thiols, ethers, thioethers, and esters. Let's start with carboxylic acids. A carboxylic acid is a compound that has a carboxyl group in it, which is this carbon double bonded to oxygen with an alcohol attached. And then there can be any group coming out of the rest of the chain. So this part here is our carboxyl group. General formula for a carboxylic acid is the carboxyl group with an R attached to the other carbon. R can mean any alkyl chain, such as this. Now we use the same prefix system when naming carboxylic acids, but because the carboxyl group will always be at the end of your carbon chain, you should start your carbon 1 from here. So we have a 6-carbon chain. The prefix for 6 is hex. Attached to this prefix, when we name carboxylic acids, we put anoic acid at the end of the name. If there were any substituents, they would go in the beginning. For example, if I had a methyl on carbon 5, I would have 5-methyl hexanoic acid. You don't have to indicate which number the carboxyl group is on because it's usually going to be numbered from carbon 1. Keep in mind that carboxyl, which is this whole group, and carbonyl, which is just this group, are two different things. It's possible that we may also have 2 carboxyl groups in one shape. We have this as one carboxyl group and this as another. Numbering these gives us carbon 1 here and carbon 2 here, because remember, this is a carbon to oxygen double bond and the carbons are usually not drawn in. We could also have numbered carbon 1 here and carbon 2 here. Because the shape is symmetrical, it doesn't matter which carbon gets the number 1. The prefix for this is going to be F, because we have 2 carbons. When we name 2 carboxylic acids in one shape, we need to use di. Recall that we also use di when we have 2 of the same substituents in a shape, such as dimethyl or diethyl. When naming a double carboxylic acid, we are going to name the main chain as an alkane. So if we just looked at these 2 carbons, it would be ethane. But we put a di right before the name of the oic acid, because this signifies we have a carboxylic acid, di signifies we have 2 of them, and ethane is how many carbons are in between those 2 groups. So this is ethane dioic acid. Any substituents we have would come at the beginning, just like we usually do. Now let's talk about the different properties of a carboxylic acid. This carboxyl group has hydrogen bonding. Recall, hydrogen bonding is when you have hydrogen connected to an oxygen, a nitrogen, or a fluorine. And in this case, it's a hydrogen to oxygen bond. We have hydrogen bonding in this shape as well as this carbon to oxygen bond being polar. Because of this, carboxylic acids are polar and would be soluble in water. However, the hydrocarbon alkyl chain, R chain, in this case our 6-carbon chain, this is the nonpolar part of the shape. So the longer the R chain, or the alkyl group, the less soluble the shape is going to become because of this increasing nonpolar part of the shape. So the solubility of the carboxylic acid overall will decrease with increasing hydrocarbon chain. Now if we look at the boiling point of a carboxylic acid, we have hydrogen bonding within the shape, and not every functional family has that. This highly increases the intermolecular forces within the compound, making it harder to break apart and giving it a higher boiling point. For example, the boiling point of hexanoic acid is 205 degrees Celsius. Comparing this to the boiling point of 2-hexanone, which is a ketone, it has the carbonyl group but not the alcohol group. The boiling point of this is about 127 degrees Celsius. So you can see that adding this alcohol group really increases the boiling point by a lot. So the boiling point of a carboxylic acid increases because hydrogen bonding. Carboxylic acids usually have strong odors. For example, you may be familiar with the smell of vinegar. It's a pretty strong smell. And this is because vinegar has ethanoic acid in it, about 5 to 8% by volume. Or if you smell rancid butter, for example, this contains butanoic acid, which is responsible for the smell. So the odors are usually pretty strong. Now let's move on to alcohols. Alcohol groups are OH groups, and we can have primary, secondary, or tertiary alcohols. Depending, and to determine this, we have to look at the carbon that the alcohol group comes out of, and how many other groups are coming out of that carbon. For example, this is a primary alcohol. So let's take a look at these examples. So I have highlighted the carbon that the alcohol is coming out of in red. Now you have to look at what other groups, aside from the alcohol, these carbons are attached to. So this carbon also branches out into this group here. And that's why this is a primary alcohol. This carbon branches out into this group and this group, so it's secondary. And this third one branches out into this group, this one, and this one, so it's tertiary. You can also take a look at the number of hydrogens that are attached to the shape. Although the hydrogens are invisible if you draw them in, carbon usually makes 4 bonds, so in order to fulfill 4 bonds, this carbon must have 2 hydrogens coming out of it. And when that's the case, you have a primary alcohol. We have 1 hydrogen coming out of this carbon and 0 hydrogens coming out of this carbon. Because remember, carbon needs to make 4 bonds to be satisfied, and you would have 1 more hydrogen filling this spot to make 4 different bonds. And here, there are already 4 bonds being made, so there's no room for hydrogen. When you have 1 hydrogen coming out of the alcohol's carbon, you have a secondary alcohol. And when you have 0 hydrogens, you have a tertiary alcohol. So you can count the number of hydrogens or the number of other chains coming out of the carbon that contains the alcohol. To name alcohols, we use the ending "-ol", and we have to indicate what number the alcohol group is on, because it won't always be at the end of the chain like a carboxylic acid. Let's try naming these 3 compounds here. For this first compound, the alcohol group should start on the number 1 carbon when we number the shape. We will normally name this as an alkane but drop the E. A prefix of 4 carbons is bute, and if we named it as an alkane, it would be butane. But we are going to drop the E, so we have butane. Then we add OL for alcohol, and it's butanol. If you don't see any number in the name of the compound, then assume the alcohol group is on a carbon 1. But you can also put 1 in the name just to clarify. It can be 1-butanol, or you can put it in the middle of the shape, right before the OL, to indicate the alcohol group is on a 1. Now let's name this one. Now the alcohol group is here. We are going to number from right to left to get alcohol on the lowest carbon, which is carbon 2. This is a 5-carbon chain, and naming it as an alkane would be pentane. Dropping the E would give us pentane, and adding the alcohol ending gives us -ol. So this is pentanol, but the alcohol group is on carbon 2. So we write 2-pentanol, or you can put the number right before the OL, so it becomes pentan 2-ol. Now let's take a look at this one. We can number it right on here. Our alcohol group comes on carbon 3. If we number right to left, it will still be on carbon 3. So it doesn't matter which way we number it. This is again a 5-carbon chain, and doing the same thing we did earlier, we would name it as an alkane but drop the E, so it's pentan instead of pentane. Then we add OL, and we put the number that the alcohol is on, which is a carbon 3. This is our main chain, with the alcohol coming out of it. But we still have a methyl substituent here that we have to name. This methyl is on a 3. So it is a 3-methyl, 3-pentanol. The 3 right before the pentanol indicates that the alcohol group is on carbon 3. It could also have been 3-methyl, pentan, 3-ol, where the 3 goes right before the ol to indicate that the alcohol group is on carbon 3. And then there would be no space or dash between the name of the substituent and the main chain. Sometimes you can have 2 alcohols in the same shape. And instead of putting ol at the ending, we put diol. Again, di because it's 2. If it was 3, you would put tri, and so on. Numbering this from right to left or left to right won't make a difference because the alcohol groups will always fall on carbons 2 and 3. We have a 4-carbon chain, which is butane if named as an alkane, and we don't drop the E because our ending does not start with a vowel. When we had regular alcohols, it started with an O for the all ending. This would make 2 vowels next to each other, and in English grammar, we usually avoid that. But now we have di-all ending, so we don't drop the E, and we just add the diol. To indicate the numbers of the alcohols, we put 2, 3 in the beginning. We can also put the numbers in the middle, so we have butane again, keeping the E, 2, 3, diol. Now, if we look at the properties of alcohols, if we look at a regular alcohol, the solubility follows the same reasoning as carboxylic acids. We have this OH group, which has hydrogen bonding within it. That makes the shape polar, but the rest of the hydrocarbon chain is not. And so the general formula for an alcohol is ROH. R can be any alkyl group. The shorter the R chain, or the hydrocarbon chain in an alcohol is, the more soluble it will be in polar solvents, because this is the polar part of the shape, and this makes it more non-polar. So this shape is going to be more polar in something like water compared to this. Now, if we look at the boiling and melting point, the same reasoning comes up as earlier. We have hydrogen bonding within our shape, which causes a very strong intermolecular force within our compound. This makes it harder to break apart, and the boiling points and melting points will be higher than a compound that does not have hydrogen bonding. For example, comparing the boiling and melting points of pentane versus pentanol, they are both 5-carbon chains, but pentanol has this alcohol group in it. The boiling point is about 137 degrees Celsius compared to without the alcohol pentane, for which the boiling point is only 36.1 degrees Celsius. And comparing the melting points, the melting point is also less negative, which is a higher number, compared to pentane, which melts at a much lower number. So hydrogen bonding in a compound will always increase your boiling and melting points because it increases the intermolecular forces in your compound. Now let's talk about viscosity. If we think of something like water versus maple syrup is more viscous because it's harder and much slower to pour than something like water. The viscosity of alcohols increases with size. So something like this would be less viscous than something like this. Lastly, the flammability of alcohols. Flammability is the ability of a chemical to burn or ignite. The flammability of an alcohol increases with a smaller molecule because there are less covalent bonds to break in order to burn it. So the smaller the molecule, the more flammable. Now let's take a look at naming thiols. These are also sometimes called sulfur alcohols because instead of an OH group, it's an SH. This is the thiol group. So to name a thiol, we name it as an alkane plus the number that the thiol group is on plus the word thiol. For example, this is a 3-carbon chain with the thiol group at carbon 2. This becomes propane 2-thiol, or something like this, which is a 4-carbon chain. And the prefix for 4 is bute, naming it as an alkane is butane. And the sulfur group is on carbon 1, so this is a butane 1-thiol. We can also put the number in the beginning, like we did with alcohols, to give 2 propane thiol or 1 butane thiol. Looking at the properties of a thiol, they usually have a very strong odor, sometimes similar to onions and garlic. The lower the molar mass or molecular weight of a thiol, usually the stronger the smell. For solubility, the SH group does not have hydrogen bonding, so it is not as soluble in water as an alcohol would be. Now let's take a look at ethers. An ether group is one that has a fused oxygen into the ring. So we end up naming our chain by separating it into the left side of the oxygen and the right. There are a couple different ways to name ethers. The first one is the alkyl ether method. For example, if we were to name this compound, because we have no other substituents, our carbon 1 is going to be starting from the carbon closest to the oxygen. We name both groups as alkyl substituents. A 1-carbon chain on the right is a methyl, and a 2-carbon chain on the left is an ethyl. We then put them in alphabetical order, and ethyl comes before methyl. Because E comes before M, we leave a space in between each word, so we have ethyl methyl. And then we put ether at the end. So this is an ethyl methyl ether. What if we have something that has 2 of the same groups on both sides? This is an ethyl group on both sides here. So instead of writing ethyl ether, we put a di to indicate that there's 2 of the same groups. This is a diethyl ether. Next we have the alkoxy method. Numbering our chain, we have 3 carbons on the right and 2 carbons on the left. The longer carbon chain is going to be named as an alkane. So 3 carbons named as an alkane is propane. The shorter chain is just going to use its prefix without the ane at the end. So this is not an ethane, it will just be F. In the middle of these, we put oxy to indicate that it's an ether. So this is ethoxypropane, one word. If there were any substituents, they would have to come before the main chains. For example, taking a look at this shape, we have a methyl group on carbon 2 and the ether group on carbon 3. I numbered it from left to right because alkyl groups are higher priority than ethers, so the methyl should be on the lower number. Now coming out of the oxygen, we are going to separate the left and the right groups. This entire chain can be considered to be coming out of one side of the oxygen, and this is coming out of the other side, which is a 2-carbon chain. This side is obviously the shorter side, so we put F with an oxy next to it, just like we did earlier. And the rest of the chain, the longer side, is going to be named as an alkane. Well, this alkane is a 4-carbon chain with a methyl coming out of it. So this is named as 2-methyl-butane because it's 4 carbons and there's a methyl on the 2. Oxygen is kind of coming off as a substituent rather than just directly being in the chain like this one. So because of that, we are going to put a 3 in the beginning to denote that off of our butane chain, we have the 3-ethoxy kind of as a substituent coming out of it. So this entire chain would be named 3-ethoxy 2-methylbutane. The third method to name ethers is called the oxa method. In this method, we count all of the atoms in our chain, including any carbons and hydrogens, and count across for the longest chain. This would be a 5-atom chain. We number the location of the oxygen and put an oxa next to it, kind of like a fused substituent. And then we name the main chain as if it was a 5-carbon chain, which is pent for 5 carbons, ane. We name it as an alkane. 3-oxapentane. Now let's take a look at the properties of ethers. Ethers are usually pretty pleasant smelling. Sometimes they can be used for perfumes or other fragrances. At room temperature, ethers are usually gases. If they're liquids, they will be very volatile liquids, so easily evaporated. They are usually colorless and weakly polar because they don't have any hydrogen bonding or any superpolar groups in the compound except this oxygen to carbon group. They will have lower boiling points when we compare it to alcohols because the alcohol group once again has the hydrogen bonding in it. So the boiling and melting points are going to be lower than that of alcohols or other groups that have hydrogen bonding. Solubility in polar solvents has the same reasoning as it did for the other compounds. The longer the nonpolar part of the chain, or the hydrocarbon chains, the less soluble our shape is going to be in polar solvents like water. There's something interesting to note about ethers. Although the hydrogen bonding is not within the ether itself, they can hydrogen bond with another water molecule. And because of this, they can end up having the same solubility as an isomeric alcohol. Remember, isomers are compounds that have the same formula but different connectivity. If we look at C2H6O, this can be an ether with 2 carbons and 6 hydrogens coming out of these carbons. Or it can be an alcohol made of 2 carbons, and we have a total of 6 hydrogens on it as well. 2 on this carbon, 3 down here, and 1 over here. Now this ether, because it can hydrogen bond with other water molecules, will end up having the same solubility as this isomeric alcohol, which is an alcohol with the same chemical formula but different connectivity, because now it's an alcohol, not an ether. Moving on to thioethers. These are the same thing as ethers, but instead of an oxygen fused in the ring, it's a sulfur. And these are also called sulfides. Just like ethers, we have a couple different ways to name these. We can use the alkyl-alkyl thioether method. To do this, we again number outward from the sulfur on both sides, when we name them in alphabetical order as substituents. So this 2-carbon chain would be named an ethyl, and this 1-carbon chain is a methyl. E comes before M, so we have ethyl methyl sulfide, where we name both alkyl groups and the thioether group, which is a sulfide group, at the end. We can also name it using the alkyl thio method. Similar to how we named the ether, we will name the longest side of the sulfur as an alkane. This is a 2-carbon group, and naming it as an alkane is ethane, which is the main chain. The other shorter chain is named as a substituent, which is methyl, and in the middle we will put thio to indicate that it separates the ethane and the methyl groups. So methyl thioethane would be the name of this compound. The last way to name sulfides is by using the thio method. With this method, we number all of the atoms in the chain, including the sulfur, just like we did with the third method using ethers. We have a 4-atom chain, and the sulfur falls on atom number 2. So we indicate the sulfur using a thio. We name the main chain as if we were numbering a carbon chain as an alkane. So this would be 2-thiobutane. Looking at the properties of a thioether, they are usually very smelly, but at certain concentrations, such as 30 to 100 ppm, parts per million, they can take on what's called a sickeningly sweet smell. The color is usually colorless, and the phase at room temperature, they're usually gases. If we have very low temperatures or very high pressures, it can become a liquid. Lastly, let's cover esters. Esters are similar to ethers, but they have a carbonyl group in the chain next to the oxygen. So this entire group is going to be the ester group. Numbering these is the same as ethers. We usually number outwards from the oxygen, counting the carbonyl carbon on this side as carbon 1. The side that does not contain the carbonyl chain, which is our right side, is going to be named as a substituent. It's a 2-carbon chain, so it's F, and we put YL to indicate a substituent. Then we will leave space and name the left side of the chain. We name it as an alkane, but we drop the E. A 4-carbon chain is butane, but dropping the E gives us butane. And then we add the ending of the ester, which is O8. So we have ethyl butanoate. Any substituents would come before the names of the main chain, but these 2 chains should be separated by a space. Now let's take a look at the properties of esters. Solubility follows the same rules as it did for our previous compounds. Carbon to oxygen bonds in our shape are polar, but the hydrocarbon chains are not. Therefore, the longer the hydrocarbon chains in our compound, the less soluble it's going to be in a polar solvent like water, because the nonpolar part of the shape is increasing. So usually esters like this with a lower molar mass are more soluble in water. Now with boiling and melting points, these shapes do not contain hydrogen bonds within them. So the boiling and melting points are in between those of an alkane and an alcohol. Taking a look at the boiling points of all three of these compounds, the boiling point of pentane, this 5-carbon alkane, is 36.1 degrees Celsius. A little higher than that, methyl butanoate here, this ester, it has a boiling point of 102 degrees Celsius, and pentanol, a 5-carbon alcohol, boils at 138 degrees Celsius. The melting points should also follow the same trends. So alcohols will always have a higher boiling point and melting point than esters because of their hydrogen bonding, whereas esters do not contain those bonds. However, they are more polar than alkanes because they have the carbon-oxygen bonds within them. So that's it for today. If this video helped you, please leave a thumbs up. And if you have any questions, leave them in the comments section below. I will leave a link to the related blog post for this video. Thanks for watching.